Muito obrigado. Senhoras e senhores, nós chegamos neste momento ao momento da última palestra do 12º Simpósio Técnico de Incubação, Matrizes de Corte e Nutrição. Para coordená-la, convidamos o empresário e consultor técnico de incubação Ivonei Francisco Socha, da Avícola Ninhada. Muito obrigado. E para falar sobre os desafios da incubação, nós convidamos a diretora global de incubatório, de desenvolvimento e suporte da Aviagem, Dinah Nicholson. Dinah Nicholson começou a trabalhar para a Aviagem em 1985, depois de completar seu PhD na Universidade de Nottingham. Durante sua carreira com a Aviagem, ela iniciou manejando os programas experimentais de matrizes incubatório e frangos, trabalhando como especialista de frangos e incubatório no Reino Unido. Também manejando a equipe de suporte técnico para clientes Ross na Europa. Em 2008, Dinah assumiu um novo projeto para comandar o grupo de especialistas de incubação global da Aviagem. Hoje, ela comanda um time forte de especialistas que trabalham com os gerentes técnicos locais para entregar aos clientes suporte técnico frequente e apropriado aos incubatórios. Please.
Thank you very much. I'm just waiting for my throne here. Well, thank you very much.
Okay.
Okay. Got a pointer?
Pointer this.
Okay. And I can see what I'm doing down there, which is wonderful.
These are the translation for
Okay.
each piece.
Okay. Good afternoon, everyone. Can you hear me in the translation booth? Okay. Yes. Thank you, firstly, for inviting me to come and talk to you today. I'm heartened to see as many of you left at the end of the week as there are. Thank you very much for sticking around. Now, I was asked to talk about the interaction of incubation systems and genetic selection. It's something of a hobby horse of mine that we have a lot of talk about how the changed bird needs different incubation conditions, and I want to talk to you today about some of the things that actually make a difference to incubation requirements. Now, I prepared for a slightly longer talk, so I'm going to go through some of the slides very, very quickly and just give the highlights. So please don't worry too much. It's just a lot more detail in some areas, which, if anybody is really interested, they're more than welcome to a copy of the paper. Okay. Right. Firstly, and this is one of the areas I'm actually going to cut back quite a bit, I'm just going to talk a little bit about the scope of the modern poultry industry and why we need both genetics and hatcheries. I'm going to talk about some of the types of embryo growth and incubation and the essentials of incubation. I'm going to talk about the origins of the domestic fowl. I mean, we talk about the changes that have been made by commercial breeding programs in 60 years. They are really as nothing compared to the changes made to the original red jungle fowl in several thousand. History of artificial incubation, again, I'm going to cut that bit short, and then just how much genetic selection has actually changed incubation needs. Okay, I think we all know the poultry industry. It's a global, very much interconnected supplier of chicks and chicken meat. We move both day-old chicks and finished meat around the world according to sales and contract. And so far, fortunately, we've been able to keep doing that. These are just some sample pictures of modern and not so modern broiler houses, and some of the hatcheries. Some of these are owned by Aviagen, some of them aren't, but just how varied in size and scope they can be. 2017, there were just under 540 million white-feathered parent stock females placed. That's approximately 63 billion broiler chicks, assuming 10% mortality in rear and 135 chicks per female. And there have been regular increases. That is an standard Aviagen map of where we think the numbers are. There's been quite a big increase, and that has mostly been in Asia in the last 5-10 years. Nice graph from FAO on poultry meat production consumption. You can see that USA, very high, Australia, Brazil, UK, South Africa, and then at the bottom of the pile you've got India at about 2 kilograms per head per year. I'm going to skip this bit. Right, okay. When you're talking about genetic selection, all of the white-feathered broilers, the commercial broilers that we see grown, are produced, or nearly all of them, by 3 breeding companies, and Aviagen, Cobb, and Hubbard. All 3 of them have breeding programs in both America and Europe, and then multiplication programs nearer the point of sale. And the modern broiler industry has taken chicken meat from being a very occasional luxury to being a staple commodity, and as such has improved the nutritional options of millions of people worldwide. There are people eating good quality protein now who wouldn't be if it weren't for the broiler industry. And that would not have been possible without large-scale hatcheries. And basically, hatcheries allow us to take over the work of growing the embryo from the hen so that she can keep laying eggs. If she stops to incubate her eggs every 10 or 15 eggs, then she's going to be a very, very low producer of eggs. And the industry absolutely relies on large-scale, human-assisted incubation to produce the day-old chicks we need, the right time and the right numbers. Broody hens would not be a substitute. You need some ridiculous number just to fill a 50,000 bird poultry shed. The other thing that we tend to forget these days is that separating the generations by using a hatchery has allowed us to eradicate diseases such as salmonella and mycoplasma, which has significantly improved the standard of hygiene, standard of food safety of chicken meat. Now, if we understand the principles, we can manage incubation conditions to optimize hatchability and broiler performance. And I talked quite a bit about this yesterday, so I'm not going to go into a lot of detail. And we're talking about water loss, we're talking chick yield, we're talking egg surface temperature, turning, time. Now, to the best of our knowledge, those constraints apply to all bird species. It's not just chickens. But there are some differences, and one of the biggest ones is the difference. Sorry, I'll stop back up again. There are between 9,000 and 10,000 species of bird in the world today. There are a lot of others that are extinct. And to the best of our knowledge, they range in weight from about 2 grams. One of the hummingbirds to well over 100 kilos, which is the ostrich. Egg size as a percentage of female body size is quite variable. You have chickens where they're about 2%. Some of the birds like kiwis, the egg weight is about 20% of the body weight. And one of the classic differences between the various species is the division into precocial and altricial species. Precocial birds are the ones where the chicks hatch, more or less ready to go. They're up, they're out, they're covered in down, they can start feeding. They may need a little bit of help finding food first time, a little bit of help with keeping warm, but by and large they're independent from the start. The altricial species hatch when they're very much less mature. They're the ones that are bold, they need to be fed by the parents, and they need a lot of parental care to keep them warm and fed. Their muscles and nervous systems are relatively underdeveloped at hatch, but the gut, unlike maybe the precocial species, is extremely well developed. And one of the descriptions I found was that they're described as all gut and no brain, because for the first few days after they hatch, all they do is eat and grow. That's an altricial species. I can't remember what it was. One of the martins, I think. And ducklings is an example of precocial. They're up and off and ready to go and quite happy to be productive quite quickly. If you look at the composition of the altricial and precocial species, and some of it's obvious. The altricial chicks will tend to have closed eyes, precocial will be open. Altricial won't have down, precocial will. Altricial tend to be immobile. But what's quite interesting as well is that there is a difference in the size of the egg yolk. Altricial species have a much, much smaller yolk as a percentage of the egg as a whole than precocial. The brain is much smaller at hatch in the altricial species, but the intestine is much bigger, and the growth rate is phenomenal. I'm going to skip that one. And this gives you an idea of the range and of the yolk size. So these are specific species. I don't think it really matters, but extreme altricial, you're looking at about 20% yolk as the percentage of the egg. Come down to the duck, you're up to 40%. Come up to the kiwi, you're up to nearly 70%. And that is a pretty good index of how independent those chicks will be at the point of hatch. Now, we talk a lot about hatch spread and making sure that the hatch spread is as tight as we can manage it. In zoological terms, it's referred to as synchronous or asynchronous hatching. And synchronous is where all the eggs in a clutch hatch at roughly the same time. And we would tend to think of chickens in particular as being synchronous hatchers. Although in fact, if you actually look within a clutch and an individual breeder hen, there's probably 15, 20 hours sometimes between them. And what you can see is that the egg composition will vary as the eggs are laid within the clutch, with the later eggs having a bigger yolk to give them a bit more of a head start. They tend to be smaller, so they heat up a bit more quickly. And there'll be some measure of partial incubation as the hen goes into the nest each day, which advances the time at which the embryo development starts again, and means that you can synchronize the hatch a bit better. And that's something that we've developed at Aviogen with the Spidey's technique. Chicks may also vocalize, and this is most effective in the quail, I think, where they have a sort of clicking noise, which will tend to advance the other chicks and bring them all together. Again, this is not something that's particularly effective with chickens. The eggs actually need to hatch for it to work. With the asynchronous hatching, tends to be altricial species, and about the most extreme is the barn owl, where they may be anything up to 14 days apart. Again, the egg composition varies, but on the whole, it's the earlier hatching or the earlier laid eggs that tend to be favoured. The later hatching eggs are almost sacrificial. You know, they'll give them a bit of a boost if the earlier chicks don't hatch, but otherwise they're left to do the best they can, and the egg may even be tuffed out of the nest altogether. Going back to the difference between precocial and altricial, precocial species tend to have nearly double the amount of yolk as a percentage to altricial. And at hatch, that difference persists. So even though they are much less advanced, they still have about half the amount of yolk. It will serve as some supply of nutrients, but when they need feeding much more quickly than the precocial species. And this is obviously something that we exploit when we transport chicks for any sort of a distance. So, talked again, time, water balance, turning, embryo temperature, and to a certain extent gas exchange. When you look at incubation time, Haman-Ran and Amasar published a paper in 1974, which was probably one of the first to look at the underlying physiology of incubation needs. And they looked at the figures across a huge number of species, taken from the published literature, where there was a record of both egg size and incubation time. And they found that it followed a reasonably tight pattern from, if you're going egg weight, incubation time in days. So heavy eggs took longer, small eggs took less time. But it wasn't a perfect fit. And what they then did was that they added shell conductance to the model that they were fitting. Shell conductance is the barrier that the eggshell presents to gas exchange from inside to out. And they then compared eggs of roughly the same size, but with different conductance, and predicted the hatch time and compared it to the reality. So you've got domestic chicken, egg weight of 54 grams, the common puffin, which is a water bird, 60 grams. But the puffin has a water vapor conductance about half of that of the chicken. So it actually makes much more of a barrier to water loss and to gas exchange. Chicken has an incubation time of 21 days. Sorry, reported incubation time of 21 days. The puffin, 38. So half the conductance, double nearly the incubation time. And when they fitted used their fitted equation, that came fairly close to what they were actually seeing. And then at the other extreme, much heavier eggs, the rhea at 609, the emu at 578 grams. Again, big differences in the water vapor conductance, although note that it's much, much higher for these big eggs. Incubation time varied between 40 and 58 days, and the prediction was spot on. So when you're seeing big differences in incubation time, they're not necessarily due to intrinsic growth rate. They're actually due to how fast the shell can provide oxygen to the embryo as it grows. Sorry, hitting the wrong button there. And that led to one of the more memorable charts. This was actually published in Scientific American, where they drew a line relating initial egg weight to egg weight at internal pip for a whole range of species, going from the wren up to the albatross, and they fall neatly and tidily on a straight line. So start thinking about what a modern geneticist can do to shift that particular relationship, and probably not much. Okay. What we do know is that birds will make behavioral or structural adjustments to make sure that they get that water loss to internal pip. So it's reasonably well known that if broiler breeders are kept at altitude, they tend to have a lower conductance egg than if they're kept at sea level. And this is to allow the embryo, or allow the egg, to maintain water more easily. Equally, duck eggs have very thick cuticles, very thick shells, and they're quite often laid in eggs where the inside has a lot of projecting twigs and straw and things, which tend to scrape that protective cuticle off. And commercial duck producers go to the other extreme and will usually wash eggs in a caustic solution to remove the cuticle before they're set. Turning. Eggs in a nest won't be sitting on their sharp end like we do in a commercial hatchery. They'll tend to be lying on their long axis. And the incubating adult will roll the eggs with their feet and with their beak. And if you give the chicken a chance to incubate her eggs naturally, she will do the same. Sorry, I'm just going to move on. This is data from Ellibol and Brake from the early 2000s, and they looked at presence or absence of turning at different periods during incubation. So they took periods 0 to 7 days, 7 to 14 days, or 15 to 18 days, and either turned or didn't turn the eggs. And at the extreme, when they didn't turn the eggs at all, the hatch of fertile came from mid-80s down to high 40s. So a really quite significant loss. Whereas if turning was omitted either in the middle or the last period, there wasn't a huge amount of difference. When they looked at that first 8 days, what they found again, and here I've charted it with hatch of fertile up this long axis and compared the turned and not turned in each period, you can see that the period of 0 to 2 days is probably the most important of all of that period. And if I'm talking to practical hatchery managers, I use this information to point out that if they start up a machine and the turning isn't working, it really isn't a good idea to go off and have a cup of coffee and find someone else to do something about it. It needs attention right then. Otherwise, you're going to lose quite a lot of hatch. What was quite nice when I was preparing this talk, I found a recent paper where somebody had used chalk loggers in nests of various species of gull and used it to monitor the number of times the eggs were turned. And lo and behold, I hope people can see that, but what they saw was that the number of turns was roughly 2 per hour for each of the 3 species, which is the optimal turning frequency also for domestic chickens. We tend not to go that far because wear and tear on the turning mechanisms tends to make it an expensive choice. But if you want the best possible hatchability, then you turn twice an hour, not once. So again, wild species are very close to domestic. Right, warming and cooling and temperatures. These get quite complicated because the heat output of the embryo changes. In the early stages, you've got virtually no heat output, and then as the embryo gets older, it starts to increase, reaching a plateau at about 18 days, and then once the egg pips and the embryo hatches, then it shoots off and increases. So any strategy for heating and cooling eggs in an incubator has to take account of those changes. This is a chart that was produced in 1937, where they were looking just at air temperature and saw pretty much a quadratic curve, that there were extremes where the eggs didn't hatch at all, and then a period in the middle where if you got too hot, too cold, you would start to lose hatchability. And I think this was done in a still air incubator. More recently, Sander Lorenz used data loggers, and it's wonderful how much data loggers have allowed us to learn about incubation. And he measured the embryo surface temperature in eggs in, I think they were actually past reform machines in a hatchery in the Netherlands, at varying distances from the fan. And he was able to come up with a relationship saying that there was a period of you've got eggshell temperature at 433 hours along the bottom here, and then the percentage hatch or the percentage culls. And what he showed was that you got a reasonably flat line along here, which dropped fairly rapidly after 39.5 centigrade shell temperature. And similarly with the culls, they actually started to rise after 39, and your culling rate increased very rapidly there afterwards. This was actually published in World Poultry, if anyone is wanting to find it, and it's still, you can still dig it up on the internet if you want to see it. So what's the ideal embryo temperature? This is a slightly later trial where they looked at different patterns of incubation, early, middle, late, so cool, ideal, cool, ideal, hot, ideal all the way through, or ideal, hot. And what they were able to show was that if you kept the eggs at a constant 100 Fahrenheit, then you got the best hatchability. And that this was actually with two different flock ages, eggs from different flock ages. So you need to be allowing the correct incubation time. You need to be making sure the eggs lose enough moisture, turning, heating and cooling to get a constant EST. If you move on to some of the ideas about genetics, the first thing you have to bear in mind is just how variable domestic chickens are. And we're used to seeing peas in a pod, white broilers and broiler breeders. But if you look at the rare breeds, you can see, sorry, I'm going to push on here so that I can show you pictures. That is a bantam, a Malaysian bantam species. I think there's a Japanese species crossed in there. And that has an adult weight of 500 grams. Jersey Giant, adult weight, female, we're not talking about the cockle here, of 5.9 kilograms. And then the Malay, which is a gamecock type, which is about 4 kilos, the pullet's about 4 kilos, and close to 1 meter tall. Incredibly variable. And then if you add some of the weird stuff in, you've got a chicken that is pretty much completely black, pigmented, and you've got, of course, the naked neck gene, which is used in commercial broiler production and is invaluable where you're putting birds into hot climates. So a lot of variability in there, again, before commercial geneticists got anywhere near them. Domestic fowls are very closely related to the red jungle fowl. They are still cross-fertile, and in cases where domestic fowl have been allowed to escape and interbreed with wild jungle fowl, they have created stable interbreeding populations. The natural range of the red jungle fowl is through sort of Java, Sumatra, up the Malay Peninsula, through Myanmar and into northern Pakistan. It's thought that the range probably extended further north in earlier times. There have been fossil remains found in northern China, which are unlikely to have been moved there through the through human intervention. And they're beautiful birds. They're apparently extremely wild, and if you read about them, one of the comments you see again and again is they are virtually impossible to capture in the wild and then keep in captivity. I'm not quite sure how our ancestors managed it, but they're gorgeous. It's thought that domestication has happened multiple times. The earliest archaeological evidence is in China, in a site dating back more than 7,000 years. And they were probably domesticated for use as fighting cocks. It's unlikely they were used for food at this point. And then they were, by 5,000 years ago, they were into Turkey and Greece, at which point they were used as in religious rituals and sacrifices. Now, recently, genetics has allowed us to isolate and interpret what they call ancient DNA. So very small samples and very old bones. And we're starting to see a lot more about how we think chickens have spread and what has changed since the original domestication. And I'm going to give you a couple of examples. One of which is, it is now thought that chickens from their original starting point, it's somewhere in Southeast Asia, went west into Turkey and then finally into Europe. But it's thought they also went east through Easter Island and Hawaii and into Southern America. And some of the work that's been done looking at the genes has shown that there are haplotypes that originated more or less in the Solomon Islands, which are then found on Easter Island, Hawaii, and into Peru. And they actually are thought to have arrived on mainland Southern America before the chickens that were brought in from Europe some 1,000 years later. The other one that's actually quite interesting is there was a sudden rise in the TSHR gene in European chicken stocks starting at around 1100 AD. And this corresponds to the time when Christianity became a dominant religion in that region, and specifically the Benedictine monastery rules, which imposed regular fast days when people couldn't eat meat from four-legged species, but they could eat chicken and they could eat fish. And at its height, there were fast days for something over half of each year. So the demand for chicken went up, and at that point, this gene became a derived allele, and it made the birds less aggressive, and it also reduced the age at first reproductive age. So they became easier to keep in larger groups, and the reproductive rate became better. here a picture of a jungle fowl hen with a chick on her nest, and how have we got from there to there? And from there to there. It's a hell of a change. Well, there's been artificial incubation around for the best part of 2,000 years. It was developed completely independently in Egypt and in China. And I think the key thing is that they were able to do this without thermostats, natural ventilation at best, no humidity control. It suggests that incubation process is pretty robust. I'm just going to show you a couple of pictures and then I'm actually going to move on. You've got an Egyptian hatchery here, which was sort of chambered rooms divided horizontally about halfway up and with chimneys, and the Chinese system where they had sort of troughs or baskets where the eggs were heated with rice hulls. And if anyone wants any more information on this, come and find me and I will willingly hand it over. It's fascinating, but we don't have time for it today. Oh, I will say the Egyptian method is still being used in Egypt. These pictures came from an FAO report from 2009 where they were looking to see how much of these sort of old-fashioned chickens were being produced when there was when we were concerned about the spread of AI. There was that rise in high path AI around that time. The reported hatchabilities were very similar to those reported by Roman writers about 2,000 years ago. So they hatch, but they don't hatch as well as they would in a modern incubator, which I'm sure will delight the producers of modern incubators. Oh yeah, and the Chinese system is still being used to produce embryonated eggs as a delicacy in the Philippines. I repeat this quite a lot because it's important. Right, moving on to genetic change. We've been selecting for broiler traits for, depending on which brand you're talking about and which company, somewhere between 60 and 75 years. And that selection has introduced enormous changes in growth rate, in meat yield, and in feed conversion. And it tends to be assumed that those changes are also seen in the embryo. So if you've got these fast-growing lines, then those lines must also be growing faster in the egg and therefore producing more heat. Now, I want you to think about the logic of that when the red jungle fowl takes 21 days to hatch and the modern broiler takes exactly the same time. They're not that much faster, but we'll go into a bit more detail in a minute. These are just some pictures. It was from a paper by Martin Zuidhoff from University of Alberta, and you can see that if you look at control lines, the birds are not only smaller, but they're much narrower than these were two modern broiler lines. One I think was a male line, and one was the modern broiler. I can't remember exactly. 57, 78, and 308 broilers, that's right. And we actually did, we have, Aviagen keep some lines that we haven't selected, we've just random bred since the early 1970s. And there's a similar change. Body weights at 42 days in 2005 were 2.7 kilos. For the 72 broiler, you're looking at 1.2 kilo. So slightly under half. Breast yield, equally different. Livability, for all that we talk about how vulnerable the selection makes, actually very similar. Egg production has improved. When I think back, I started working for Ross Breeders in 1985. We see much better peaks out of the Ross 308 in 2018 than we ever did in 1985. Genetic egg size has stayed much the same. In the hatchery, we still need 21 days to incubate eggs. They still need to lose 12% of their weight, and the chick yield at hatch ideally is still around 67%. The various stages of embryo growth identified by Hamburger and Hamilton in 1951 still happen on the same day of development. No sign of acceleration. That poster's available for free on the internet if anyone wants to download it. And I think what we have to be realistic about is if it's still taking 21 days to hatch, maybe it's the differentiation of the tissues that is time-bound rather than anything else. And we need to be careful about how far we think things are going to change. Has the heat production changed? Now, there was a paper published in 2004 by Janka and, oh goodness, I've forgotten her name, never mind, where they compared the heat output of Ross 308, Ross 508, and a commercial layer line. We've also got data from earlier. Steve Tullett did some work with Charles Deeming and Fiona Burton in the early 1980s. And we have more recent reports from Ampai Nangsai, which were published in 2014, 2015. If you plot the heat output, and in this case we're going to talk about oxygen consumption, but the two are directly related, they are actually very, very similar. I'm sorry, the package has actually relocated a couple of things, but when you look at Janka's 3 lines here, Janka's two broiler lines here, they're very much on the same line. The 2 Tullett papers can be inserted here, and Ampai's 2014 data actually lies on exactly the same point. So over 30 years of change, the plateau heat production in these birds hasn't actually changed. What is different is the layer. And the reason it's different is it's got a thicker shell, so it doesn't allow as much oxygen in, and it's got a smaller yolk, so it hasn't got as much fuel for the embryo growth. There was a experiment done in Canada in the early 2000s, which was published under O'Day et al., which seems to have got lost. I'm not quite sure why, but she compared the 1978 control line with a equivalent of the 708 and an equivalent of the 308. She didn't actually specify which breeds she used, and I'm not 100% sure which ones they were. But what she found was, you've got here the genetic control line, the body weight line, and the breast yield line. And there was a small technical significantly different here, where in fact I think the 78 line was running hotter than the others. But if you compare those lines up to 19 days, there is no significant difference. Okay. So what drives heat output? Oxygen availability through the shell, so shell conductance. And commercial layers have been selected for thick, non-porous shells, food packaging, and so tend to have a lower heat output than broilers. The fact that they're also smaller is actually coincidental in this particular discussion. There are some small differences between broiler lines. Ampi found minor differences between Ross and Cobb, but they're not huge. But embryos in large eggs will certainly produce a lot more heat than embryos in small eggs. And if you look, this was a paper done by Lawrence et al., where by about 13 days, small and large eggs were differentiating, and the big eggs were producing significantly more heat than the small eggs. And in fact, O'Day saw something similar when she compared 33-week with 36-week-old parent stock production, where there was a significant difference all the way through. The difference wasn't due to genotype, it was due to egg size. So far as we can see, there's no real indication for the Ross 308 that all our continuous selection for post-hatch characteristics, for growth, for meat yield, for feed conversion, etc., has had any significant correlated effect on pre-hatch. What I would say is that in all the time that we've been selecting, we have been running commercially standard incubation programs. We incubate for 21 days, we take the chicks out, we place them. Even if there was a tendency for the chicks to grow, to hatch faster, if that was happening, the pull at 21 days and placement would probably put those chicks at a disadvantage when we started looking at growth. And certainly for as long as I've been involved, we've been very, very definite that our hatchery processes need to be as close to commercial as possible in terms of temperature, humidity, and duration. What we do select on is some of the characteristics which we think will make the eggs more uniform and more able to achieve the standards that we're looking for. So where is all this heat coming from? Well, I think the first thing is, I said earlier that data loggers were a blessing. Well, the fact that we can actually measure heat means that we're thinking about it and we're looking at it. I think there is probably a tendency to produce bigger eggs. There may be better fertility sometimes. And in some cases, you're dealing with machines that are getting a lot older. So the cooling, the fan speeds, the door seals are all suboptimal. And having these modern broilers that produce more heat is maybe a useful excuse when somebody starts complaining. The other thing that makes a big difference, and I think has been behind a lot of the calls for genetic change, have been where there have been concerted efforts to increase capacity. And the initial upcry that I remember in the early 2000s certainly came when James Way had increased the capacity of their hatches. And there have been other increases since, either done by the incubator manufacturers or just as a one-off by the hatchery concerned. So if you're overheating, it's worth looking for that first. And of course the broiler has less time to recover, and nobody's denying they grow more quickly to their target weight. So if you get things wrong, then you're not going to have an awful lot of time to get things, but get yourself back into normal situation. What do we aim to control by selection? I'm afraid this is quite an old photograph now, but our traditional pedigree pattern was 1 cockerel and 10 hens. And we measure things like age at first egg, total eggs per hen housed, rate of lay, fertility, hatcher fertile. And then in the hatchery we look at things like egg weight, specific gravity, albumin quality, percentage egg weight loss, and of course chick numbers. And I would actually add to that list more recently, we've focused a lot more on early survival between hatch and 7 days, and we also tend to store eggs for longer so that we are mirroring normal practice in terms of egg storage. I think some of the challenges we're going to have, understanding of responses to CO2 and oxygen level. There's quite a bit of trials work, but it tends to stop at the hatcher door, so we don't know an awful lot about how it influences performance. Sex identification in ovo, huge focus on that with the layer industry, but I think broiler breeders will welcome it as well. And the effects of light in incubation. There's some very, very interesting research work. Getting it implemented practically, I think, is going to be harder. And the in-house or low-density hatching and feeding, early feeding and drinking, is something that will certainly become more common with broilers, I think. We have 2 huge challenges. One of them is disinfection without being able to use formalin, and particularly where we've had to stop using antibiotics. And the other is chick transport and delivery, when we have a lot of pressure from the welfare lobby to keep that as short and as difficult as possible. So, conclusions. We've been using artificial incubation for about 2,000 years, and in that time it's been of intense interest to scientists, not just to biologists, but one of the first thermostats was actually produced for use on an incubator that was demonstrated in the 1600s, I think. It took 21 days to produce a chick from an egg. When the red jungle fowl was first domesticated, it still does. When we look at various trials over 30 years, there's been no change in the Ross 308 heat production. But incubation will continue to develop and use new technologies. And that's one of the things that makes it such a satisfying and fascinating area of poultry production to be working in. Right, I've got 10 minutes, so I'm going to make the most of it. If you're wanting to define the incubation requirements of different lines, I've said Aviagen, you might be talking about comparisons across breeding companies. What do you look at? Again, eggshell temperature, water loss, turning. Do we need to adjust the machine settings if we get a new line? Well, possibly, if you've got big eggs. Possibly, if you've got eggs with a very high conductance. If you've got lines with high conductance and small eggs, they'll probably be quicker. This is a trial we did a while ago where we looked at different pure lines and crosses. I'd rather hoped that we would be able to come up with an additive prediction where if you crossed line Z with line Y, the progeny would be somewhere in the middle. In the event, they tend to follow the female line. But what you can see is that a significant proportion of the variability, this plots fresh egg weight against incubation time. So this is time to completing incubation. And over a whole lot of different male lines, female lines, and goodness knows what we see is that the 708 is always one of the quickest lines. This is one of the contributing lines to the 308AP, and the 308AP tends to be one of the slower lines. Part of that's egg size, part of that is almost certainly conductance. So if you've got a new product and you don't know anything about it, use your normal settings, keep a very close eye on what happens. Monitor egg weight, monitor egg cell temperature, monitor weight loss, yield, and keep an eye on the hatch time. Hatch time is actually the most likely to be different. Then you can start adjusting your settings to nudge outcomes close to the requirements for those eggs. To conclude, genetics and artificial incubation have existed side by side for millennia. It's not a new thing. Incubation and embryo development of the chicken egg has been the focus of research for several hundred years. Avigen have been breeding chickens for, well, the Ross is just over 60 years, Arborec is a bit older. In that time, the eggs have always been incubated according to current industry standards, and there have been no major changes in the incubation requirements of the lines we've got. Thank you very much for your attention. And sorry I got very croaky at the end there.
Pessoal, agradecemos primeiro a doutora Nicholson pela palestra, pela brilhante palestra, e está aberto para vocês aí alguma pergunta que queiram fazer.
Primeiramente, parabéns pela apresentação. Quando você falou sobre o efeito da luz, sobre a incubação, ela teria um efeito positivo ou negativo na incubação? E aí, como seria que deveria ser feito isso? Uso contínuo da luz? Algum tipo de espectro de luz diferente? Como é que seria isso?
Okay. It's important that you distinguish what type of light you're using. One of the things that's made it much more of an interesting, sorry, I'm going to take this off, interesting thing to study is that with new light sources, particularly the little white light sources, you can actually put them into an incubator. You can get even distribution of light with relatively low heat input. The old-fashioned incandescent lights were hopeless because they just overheated. The other thing you do have to watch is that the distribution of light does have to be even, because chicks, when they emerge, will go towards light. So if you've got a point source at one corner, they'll all go towards it and they'll smother. So it's something you need to be careful of. It's early days, I think. There's been quite a lot of research in Israel where they've looked at green light for really the sort of middle period of incubation and also into the hatch. And seen some benefits, particularly seen some benefits to satellite cell development. We're early days looking at it ourselves, haven't really managed to duplicate the small-scale trial results in bigger machines. And I think that we may not be the only ones who find that difficult, but it has some potential, and I think will be quite an interesting new area to look at over the next 10, 15 years. Okay.
Mais alguma pergunta? Eu gostaria de fazer uma pergunta à doutora Nicholson. Okay?
Yep.
Na sua opinião, a evolução genética das aves, quando, por tudo aquilo que já foi falado aqui, que precisamos da quantidade de proteína animal que precisamos produzir para alimentar o mundo, a escala é muito grande. E como que a senhora vê se a evolução genética e os equipamentos que nós temos hoje de incubação estão andando junto?
I think if we're going to get protein nutrition up for the poorer countries, then poultry, specifically chicken, is probably one of the stronger candidates to do it. Although if you look at the FAO figures, the very poorest countries, chicken is actually quite a low percentage of their total meat intake, because I think you need a certain level of prosperity before you can start mass production of broiler chickens. And clearly these countries hadn't reached that point. But it has some very, very attractive aspects to it, not least that over the years the feed efficiency has improved to such an extent that you can actually quantify how much less land you need each year to grow the feed to feed the chickens to achieve the same amount of output. They're also, of the meat-producing animals, way the lowest in terms of the carbon dioxide output. Lower even than turkeys, I think. Ultimately, I think it will be down to consumer preference. It wouldn't entirely surprise me if we went eventually to artificially grown meat, vat-grown meat, but I think that will be a long time coming. People seem to like their fresh food, and chicken is a relatively cheap and relatively attractive way of getting it. Okay.
Mais alguma pergunta, pessoal? Então, agradecemos imensamente a palestra da doutora Nicholson. Acredito que teremos alguma coisa para o encerramento.
Não, então é isso. Então é agradecer, na verdade, a presença da nossa palestrante e, claro, convidar o senhor Ivonei Francisco Socha, para fazer a entrega de um brinde à palestrante, a última palestrante do nosso evento, por gentileza. Nosso muito obrigado, então. Obrigado mais uma vez aos dois, e já encaminhando a parte final, o encerramento do nosso evento, nós gostaríamos de convidar a todos para assistirmos juntos a um vídeo, um recado final do presidente da ACAV, senhor José Antônio Ribas Júnior.
Meus amigos, nós estamos chegando ao final do nosso 12º evento da ACAV. Estou aqui para me despedir e agradecer a presença de todos vocês que fizeram do evento mais uma vez um sucesso. Mais de 550 pessoas circulando entre nós e atendendo o nosso principal objetivo, que é continuar essa trilha de sucesso, não só do nosso evento, mas de toda a cadeia de frango do Brasil, toda a cadeia de frango de Santa Catarina, desse nosso evento que se tornou cada vez maior e muito bonito. Acho que todos nós concordamos que foi um evento muito bonito. Ficam temas de casa importantes. Nós temos que continuar perseverando com qualidade, nós temos que continuar trabalhando muito pela eficiência do nosso setor e muito, gravem muito o que eu tenho dito para vocês. Nós precisamos cada vez mais ser transparente, falar o que a gente faz e fazer o que a gente fala. Isso é absolutamente relevante porque assim nós vamos conquistar a confiança de todo o mercado. Este, para mim, é um dos legados que fica do nosso evento. Agradeço muito a presença de cada um de vocês aqui conosco. Infelizmente, não pude ficar pessoalmente para o final do nosso evento, alguns compromissos nos chamam, mas eu estou com o coração muito feliz de sair daqui e ver o sucesso de mais um evento nosso. E espero encontrar todos vocês daqui a 2 anos no nosso próximo evento e, com certeza, num ambiente muito melhor de frango e discutindo cada vez mais as melhorias que virão para o nosso setor se tornar e continuar sendo cada vez mais a liderança no Brasil e a liderança no mundo, fazendo um frango que todo mundo pode confiar e consumir, porque realmente é uma proteína de altíssima eficiência e barata para todo mundo. Esse é a nossa contribuição para o mundo. Agradeço muito vocês, um grande abraço e até daqui a 2 anos.
É isso aí, gente. Reforçando então o agradecimento a todos os presentes. Imaginamos que tenham sido alguns dias aqui juntos de muito aprendizado. Esperamos que sim. E já estamos pensando, claro, no próximo simpósio, 13º programado para o ano de 2020. Nosso muito obrigado mais uma vez. Quem vai retornar para as suas cidades, vai pegar a estrada, claro, um bom retorno com muito cuidado. Quem vai estender a permanência em Florianópolis, aproveitem demais a nossa cidade. Obrigado. Uma ótima tarde a todos.